Thank you, Evelyn, and good morning to everyone. Welcome to today's webinar titled Soil Water Sensors for Agriculture, Theory and Issues. My name is Peter Robinson, and I am the moderator for today's webinar. I work at the West National Technology Support Center in Portland, Oregon as the Water Management Engineer. This webinar is the first of two webinars on soil water sensors that Dr. Steve Evatt is presenting. The second webinar is on February 11th. The second webinar is titled Soil Water Sensors for Agriculture, Applications and Usefulness. Please let your colleagues know about the second one. You can access the information for the second webinar on your screen now. Look in the pod labeled today's links, and the link is called February Webinar on Soil Water Sensors. I want to remind everyone on your screen that you can find a section called Q&A. During the course of the presentation, you will be able to type in questions for Dr. Evatt, and after 50 minutes, after Dr. Evatt ends his formal presentation, I will select and read the questions to him and give Dr. Evatt a chance to answer them. Finally, it is my pleasure to introduce Dr. Steve Evatt. Stephen R. Evatt is a research soil scientist and the lead scientist with the USDA Agricultural Research Service at the Conservation and Production Research Laboratory in Bushland, Texas. He is a graduate of the University of Idaho and the University of Arizona. He's the author or co-author of 245 publications, including 25 book chapters. You can find more details about Dr. Evatt's career on the PDF of the slideshow, which is available in the today's handout pod that's on your screen now. Now I'd like to turn over the presentation to Dr. Steve Evatt. Steve, you have the floor.
Thank you, Peter and Evelyn, and good morning to everyone. I'm not going to dwell on my qualifications except to say that I started using soil water sensors, specifically the neutron probe, in 1980, and have been working with them and trying to develop new sensors that are more capable and easier to use since then. The premise of today's presentation is that if we are going to recommend soil water sensors and sensing systems, we should know how they work and where, when, and why they may not work and may not work well. Soil water measurement and sensing are two different things. The measurement methods are typically too difficult and time-consuming for people to routinely use. They involve taking soil samples, which may have a defined volume or not, and drying them typically in an oven. Sensing methods, which are what most of us use and most producers use, involve measuring some response to an applied force or radiation. And that radiation may be electromagnetic or particle radiation in terms for the neutron probe. And the water content is estimated from the measured response using a calibration. Measurement involves samplers, such as you see in the upper right corner, to get a volumetric sample. They can also involve disturbed samples using an oak field probe, a shovel, or an auger. In both cases, we weigh those, we dry the samples, we weigh them again to get the water that was in that sample. If we have a disturbed sample, we end up with units of mass per unit mass, grams per gram, for instance. And if we use a volumetric sample, we know the volume of a gram of water is 1 cubic centimeter, and we get volumetric directly by dividing by the sample volume. It is important to understand that if we get a mass basis water content, converting it to volumetric using an assumed bulk density is not recommended and can lead to some rather large errors. The field and appearance method that we have used for a long time can be useful, but I don't know anybody that really has the time to do this anymore, and it is not a measurement. The sensor types that we typically see in production agriculture are the soil water matrix potential energy sensors that are the resistance blocks and tensiometers, and the water content or permittivity sensors that include the neutron sensor, which does not respond to permittivity, and the capacitance sensors and travel time sensors that do respond to the permittivity of the soil, which is a property of the soil that is dependent upon its water content and several other factors that we'll discuss here in a minute. There are also the electrical conductivity sensors, such as the Veris EM38 and even TDR systems. Electrical conductivity can be a stand-in for water content, but it is not an accurate way to get a water content. Soil water units, if we're looking at matrix potential sensors, are in kilopascals or bars. Often we'll see for tensiometers, for instance, readings in centibars. Water content sensors give us or attempt to give us a volumetric water content, which we can have as meter cubed per meter cubed or foot per foot. These have the same value. In both cases, they're a dimensionless fraction. The electrical conductivity sensors, of course, give us readings in decisiemens per meter. All sensors measure a surrogate property that is then related to water content, theta sub B, through a calibration. The major surrogate properties are capacitance, in which we have a circuit that measures a variable resonant frequency. The circuit resonates at a frequency in proportion to the water content, actually inversely proportional, such that as water content increases, the frequency decreases. The phase delay sensors, of which there are very few, and the travel time sensors, including the quasi-travel time sensors that attempt to measure a travel time but do it incorrectly, and the true time domain reflectometry and transmission sensors that actually measure the correct travel time. And of course, there is also the thermal neutron count. I am not going to spend a lot of time today on the neutron probe, but it is still being used by consultants in places like California for very high value crops, such as wine grapes. The neutron probe contains a slightly radioactive source of fast neutrons, and those neutrons are thermalized by interactions with hydrogen in the soil and are counted by the detector. It poses a negligible health hazard, but it is very highly regulated nonetheless, and because of that, it requires safety training, licensing, and becomes expensive to use, mostly because it cannot be used unattended and therefore requires a lot of labor. It's used a lot in research. It's quite accurate when calibrated. Importantly, it has a larger sensed volume than other sensors, which can lead to better data showing what the crop water uptake actually is. We don't see much use in production agriculture. And here's some pictures of what these sensors look like. The old TDR systems shown in the upper set of photographs are not used in production agriculture, but still used in research. There is a new compact TDR device that is beginning to see use in agriculture. Then there are the frequency domain sensors, and there are quite a few mixed technologies that are neither one or the other. And the so-called frequency domain reflectometers are an example. All electromagnetic sensors respond to the apparent permittivity, epsilon sub A. I don't expect anyone to understand this equation, but simply to recognize the components of it and why they're important to the measurement system. The epsilon prime, just to the right of the equal sign, is the real permittivity, and that is what responds directly to the water content of the soil. But the sensors respond to the apparent permittivity, which is a combination of all the factors in the right-hand side of this equation. The reason this is important is that there are two factors, highlighted in yellow, that exist in all soils to various degrees and which can bias the readings of a permittivity sensor. One of these is the epsilon double prime with relax in subscript. That's the relaxation due to movement of water molecules, or they're relatively non-movement when they are attracted to soil particles. So in high surface area soils where the polar water molecule cannot rotate freely, we get a large value of this epsilon subrelaxation. The other factors are the bulk electrical conductivity, which is sigma dC, and the frequency of the reading.
This is Evelyn. I'm sorry to interrupt your presentation at the moment. We've gotten a few comments that we're having some audio issues, so we're going to take about a 60-second pause and restart the meeting audio so that the participants can have a better audio experience. If you could just hold on about 60 seconds, we'll get you back online.
Let me know.
Thank you, Evelyn. The bottom line in this equation is that clay particle density and the amount of clay in a soil will affect the readings of these sensors, and that the bulk electrical conductivity and the frequency of measurement will also affect the apparent permittivity regardless of the water content. And we see this as interferences in the water content reading. Now, the capacitance sensors are very important in soil water sensing. Almost all of the sensors that are sold today are some sort of capacitance sensor, either the ones that go down a plastic access tube or ones that are inserted into the soil. Capacitance is the ability of a body to store electrical charge. And in a capacitor used in an electronic circuit, we have two plates, and the equation for capacitance is quite simple. It is the relative permittivity multiplied by the permittivity of free space, a constant, multiplied by a geometric factor, G sub m. In a capacitor used in electronics, the area of the plates and the distance between them is very closely regulated, and the area is much larger than the distance between the plates. In this case, the geometric factor equals A divided by D, and we know very closely what the capacitance of that capacitor is. You can see here the electromagnetic force between the capacitors, and the fringing field goes outside of those two plates. Well, when the area is very large, the fringing field is negligible. So we know what the capacitance of a capacitor in an electronic circuit is. But in a soil, we have many complicating factors. Because the soil is a mixed medium, it is subject to the relaxation permittivity, which is a fact, depends on the frequency of measurement, and also it is subject to the bulk electrical conductivity divided by the frequency of measurement. The effects of relaxation and bulk EC are important at the relatively small frequencies of capacitance sensors. This frequency decreases as water content increases, so the measurement itself is changing the frequency, which compounds both of these effects. This is a resonant oscillator circuit such as is used in capacitance sensors, and only the very bottom capacitance, the C sub epsilon, is the fringing capacitance that involves the soil itself. And you can see that the resonant frequency here, omega, is equal to the sum of capacitances inside the circuit, actual capacitors, and this fringing field. When we have a uniform medium, and what we see here is we see a Syntec type double ring capacitance sensor in an access tube, and we have a uniform medium outside of that, and you can see the field lines in the upper diagram are very uniform. But it has been found experimentally and theoretically that when we have a conductor close to the outside of that access tube, it distorts that electromagnetic field, and we get a different frequency of measurement. even though the environmental material has stayed the same. What happens in a field soil is that we do not have uniform geometry. If we calibrate a capacitance sensor in a soil column that we've repacked, we have a very uniform soil in that soil column, and we get a certain calibration. But when we put that sensor in an access tube in the soil, it is surrounded by soil with structure. Soil that has different sized PEDs all around the access tube with different water contents, different bulk ECs, because water content and bulk EC go hand in hand. And what we see is the more conductive PEDs attract the fringing field, which is a minor part of the electromagnetic field. And we therefore do not get a uniform examination of the soil around the access tube. This gives us a different frequency, resonant frequency, and a different water content reading, even though the bulk water content in the soil may be the same as in the top diagram. And small-scale variability is very important in many soils, and here's simply this is a soil pit that's been left to dry a little bit so you can see where the PEDs are and the cracks. Every crack and every line of separation between PEDs is a capacitance plate, essentially. And this field is going to be disturbed by how it goes into the soil outside the access tube. Now, what you see drawn here is the actual size of a capacitance sensor in the access tube and the actual size of the field, the maximum size of the field in the soil. When the soil is wet, this field becomes much smaller. So since 1994, when we first worked with NRCS on this question with the some of the older capacitance sensors, we've had a steady progression of understanding how this geometric factor causes our capacitance sensors not to correctly report what the water content is. We followed on that first study with a 5-year study with the International Atomic Energy Agency, in which we compared capacitance, TDR, and neutron probe measurements, and judged only the TDR and the neutron probe as being suitable for irrigation scheduling. Between 2006 and 2012, our laboratory and cooperating laboratories across the nation obtained confirming evidence and theoretical understanding of this capacitance sensor sensitivity to non-uniform soil and the sensing volume. So that I will revisit here in a minute, but I want to move on to time domain measurements, which are distinctly different because they obey a different set of equations. They obey Maxwell's equations, electromagnetic equations. And the velocity of an electrical pulse put down an electrode in the soil is related to the square root of the permittivity. There is no geometric factor in Maxwell's equations, and the time domain methods are not disturbed by the geometry of the soil around the probe. If the pulse rise time is short enough in these methods, then the frequency omega is very large and electrical conductivity effects are quite small, because this ratio of the bulk EC, sigma DC, divided by the frequency becomes quite small. And temperature effects on the relaxation permittivity are also small at the frequencies used in TDR and TDT measurements. But measurement of time, travel time, was very difficult until recently, when the Acclima ACC TDT, time domain transmission sensor, and the TDR 315 were introduced. And here's just an example of a purpose-built TDR probe was made to work in this soil pot. And a lot of very good research was done with this, but these systems weren't useful for production agriculture because they were so complex, expensive, and difficult to use. In this diagram here, what we see is a conventional TDR system. It consisted of an $8,000 Tektronix cable tester, a $1,000 notebook PC, several $1,000 multiplexers, and a bunch of TDR probes attached to that, and supporting power supplies because the sum power consumption was some 2 amps at 12 volts DC. These simply were not useful in production agriculture, no matter how accurate they were, which is why what we see on the market today, up until this year, has been almost completely capacitance sensors. I'll get down to why this is relevant at the end of this discussion. I do want to show you a TDR waveform. On the left of this, you see the level of the voltage in the coaxial cable inside the TDR instrument. You see the voltage step that's injected. The rise time of this is about 150 picoseconds, very fast. And then you see the reflection from the probe in the soil. And here is the reflection from the probe in the soil. Above it, you can see the TDR probe. And what we're seeing is we see a reflection from the handle of the probe, and we see a reflection of this step pulse at the end of the rods, because these rods are not connected to each other, and that's an open circuit. So this reflection is what we try to determine, that time 2, and we get the time 1 here, and the difference is the travel time. That is proportional to water content in linear fashion. And several different computer programs were developed over the years, beginning in the late 1980s and 1990s. And this is an example of automatic waveform interpretation using one of these programs to find the travel time. This has become very well done, very reproducible. Now, Top and Reynolds proposed that their polynomial equation published in 1980 could easily be linearized so that water content could be seen as a intercept term, a slope term, and the square root of the apparent permittivity. And what we're actually measuring with travel time systems is the travel time, T, or T sub T, and it's actually linear in T sub T, which is shown in the second equation. That's equivalent to the first equation. This is important because if we have a linear relationship, then we can calibrate at the wet end and the dry end and not have intermediate soil samples, and it becomes much easier to calibrate sensors. Without calibration, accuracy of time domain systems is plus or minus 0.02 meter cubed per meter cubed in most soils, agricultural soils, which is another advantage of the time domain methods. It's not true for the frequency domain methods. Issues with travel time methods, well, until recently, they were complex and expensive. Some of the so-called TDR sensors are not TDR. A lot of supposed travel time sensors have incorrect travel time measurement methods, including the water content reflectometers, as they're called. And then we have a bunch of sensors called frequency domain reflectometers, which are examples of incorrect travel time and really a contradiction in terms. These are actually more frequency domain methods than they are time domain methods, and they have all the problems that a frequency domain method such as a capacitance sensor have. And I'm going to tell you a story here now about why this is so. This is a bunch of waveforms from a TDR system and a Pullman clay loam at different water contents, theta sub V. The red line is for a water content of 0.012, and we can see that the slope of the reflection is very large, very steep, and this is because the bulk EC in this soil is quite small. For the largest water content, the line in green, we see that the slope is much weaker. It's a weak reflection. And this is because the bulk EC of this soil at this water content is 1.7 decisiemens per meter, because of its high content of superactive clay. This is a non-saline soil. This is common in a lot of our agricultural soils, particularly in the West. Well, this introduces problems unless we capture the full waveform, as is done in true TDR systems, and then interpret it using waveform analysis to get the correct time to, which is shown for both these waveforms. So with waveform analysis, we can get a correct travel time. The problem that we have is that the cheap sensors that are out there do not get the waveform. Instead, they use a voltage comparator, which is a very cheap electronic chip. And in that, they set a threshold voltage, and then they look for the time at which that reflection rises to the value of the threshold voltage. And in this diagram, I have shown you the waveform voltage within the TDR probe from time 1 to time 2, and then the reflection after time 2 at 1 bulk electrical conductivity. And what we measure with these voltage comparators is a time T3 that is not equal to T2, such that the travel time is overestimated. Furthermore, as the bulk EC changes, the slope of this reflection changes, and you can get a whole host of T3 values, none of which reflect the true travel time of this system. And this is something that cannot be corrected for. So this leads to very inaccurate water contents in high clay soils, in soils that are affected at all by any salinity, and in soils with high bulk density, for instance, and it gets worse as water content increases. Here's some examples of incorrect travel time measurement. The TRIME system from IMCO in Germany, the CS615 to CS616 water content reflectometers, the Spectrum TDR 300. None of these measures travel time correctly. We now have a couple of sensors out there that do get correct travel time and report accurate water contents. Excuse me. Some issues with capacitance sensors to summarize. The resonance frequency decreases as water content increases, while bulk EC increases with water content in all soils. The ratio of bulk EC over omega becomes larger, and the permittivity is biased to larger values. The calibration is affected, water content is overestimated, and there is no practical solution, even though some of these sensors are sold with so-called temperature corrections. The reason they have a temperature correction is the bulk EC goes up with temperature as well. The electromagnetic field propagation is strongly influenced by these small-scale variations in water content and bulk EC. The bulk density in soils is very highly variable, as is the water content at small scales, on the centimeter scale. And this is true in almost all soils except extremely uniform soils that have no structure. This causes the estimated water content to vary randomly. Spatial variability across the field is misreported. Next month I'll show you what happens there. And the data are not representative of the field or crop water use. Calibration in a lab column is not useful in the field, and this is an important result of this, because in a lab column we have a uniform soil, and we don't get a calibration that means anything in the field. The fringing field for a capacitance sensor is small outside the access tube and decreases in size as water content increases. It about goes to half of that field size as we approach saturation. This accentuates the false reporting of spatial variation in water content, and it makes tight access tube contact with undisturbed soil very important, since any void or unrepresentative soil in contact with access tube preferentially influences the reading, And very importantly, it means that slurry installations are quite suspect because the field does not go outside of the slurry around the access tube. And so we're only reading the slurry, not the real field soil. When tubes are installed using slurries in soils that have a lot of horizon differences from an AP to a BT to a C horizon, that slurry is a uniform soil, and so we get a very misrepresentative readings out of those. The other problem with slurries, while I'm on it, are that they are a low bulk density soil once they dry, and we tend to get roots following down through that slurry and taking up water at depths that it doesn't happen in the field in the real soil. Other issues with capacitance sensors include the inherently nonlinear calibration, which means we need water contents not just at the wet and dry ends, but at intermediate water contents. And the sensitivity to frequency change is much greater at larger water contents because of the nonlinearity, and this increases noise at large water contents. I want to spend a little time talking about the importance of bulk EC in soils. Bulk EC varies greatly on small and large scales and vertically and horizontally. It can be large in wet, non-saline soils if they contain active and superactive clays, as many of our western soils do, and some in the Midwest as well. The bulk EC affects permittivity more at the smaller frequencies of capacitance sensors, and its spatiotemporal variation is strongly affected by irrigation application method, and soil textural variations. I was just in California and looking at some of the bulk EC data in fields there, and the variability is extremely high, and it causes these capacitance sensors to misreport water content all over the place. Bulk EC is strongly dependent on both temperature and water content. Here's an example of 3 different horizons of one soil. The relationship between the bulk EC and the temperature is quite different in those 3 horizons. And here is the BT horizon, the green symbols in a Pullman clay loam. And we can see bulk EC is greater than 1.7 decisiemens per meter. Here's some data. Rhodes from the Salinity Lab in California did studies all over the nation looking at the bulk EC of different soils as affected by water content in all situations. You get graphs like this that show the increasing bulk EC with water content. Now let's finish up with water stress sensing, which is other kind of sensing that's common in production agriculture, especially in vegetable crops, and in some places even for corn, depending on the soil type. The soil matrix potential sensors are the tensiometers, granular matrix sensors, and gypsum blocks. The tensiometers are actually a direct measurement of the matrix potential in the soil. And the way these are used is we identify a set point for irrigation. It can be either a stop or start point, and observe the sensor readings often enough to react well. The soil energy potential, the total is made up of the matrix potential, psi sub m, the pressure potential, the osmotic potential, psi sub o, and the gravitational potential. We really are measuring the matrix potential with these sensors and with the tensiometer. Although the osmotic potential in a salt-affected soil can make that potential much more negative and reduce the plant water uptake accordingly. The gravitational potential simply affects our readings because it affects how it increases with the depth of the reading. In all soils, water moves from regions of greater potential to those of lesser potential, including from the soil to the air through the plant. And it's that very low water potential in the air of any humidity compared with soil water potentials that allows movement through plants. Some limits of matrix potential. Well, field capacity and permanent wilting point are the two we're most concerned with. The matrix potential at field capacity is about 0.1 kilopascals, and clay soils about 0.33 or a third of a kilopascal on sandy soils. This is what's left after free drainage for about 24 hours. And sometimes in clay soils we let that time go a little longer. And permanent wilting point is often taken as negative 1,500 kilopascals, but this varies greatly with texture and bulk density due to the soil-dependent relationship between hydraulic conductivity and the soil water potential and the soil-dependent rooting. And it varies a lot with the crop as well. I won't go into it, but there is some very good evidence for this that Judy Tolk has come up with. This relationship between psi and water content is highly nonlinear and hysteretic. We can measure it with pressure plate and psychrometer methods in the lab. We can use tensiometers and soil water content measurements in the field. But most commonly in practical situations, we estimate this using pitot transfer functions, computer programs. We simply don't have the time to do all the pressure plate work, and it's been done by a lot of people. And here's some typical field capacity and wilting point values for different soil textures. And one of the things that we should be looking at is that in sandy soils, the coarser soils, the plant available water at field capacity is really quite small. If we're trying to schedule irrigations in soils that have a small available water holding capacity, then we need soil water sensors that are quite accurate. And we can't get accuracies that enable us to schedule irrigations with the capacitance sensors by and large. There are other ways that we can do irrigation management with capacitance sensors, and I'll discuss those in February. I'm not trying to say they're useless. I'm trying to point out that they have some severe limitations. The pitot transfer functions are databases of soil hydraulic properties, and we can query them by providing the texture only, or the texture plus the bulk density, or if we have the sand, silt, and clay percentages, all 5 of those. And we can even add, if we know it, the water content at field capacity and wilting point. The more data we put into these, the better relationships we get between water content and soil water potential. And I've noted a couple of these that are available online. The one from Saxton was developed in conjunction with NRCS. The Rosetta one was developed at the Salinity Lab in Riverside, and both of these offer some good data. The water matrix potential versus water content looks like this for 3 soils of widely varying texture. And one of the things that we should note is that if we look at only the plant available water, which is the part that is not tinted, we see that in sand soils we have very small plant available water. And in this silt loam, we have a very large plant available water, which is why silt loam soils are so good for agriculture. And in the clay soils, which really have a higher saturated water content, the water is not as available because as the clay dries, it retains that water and doesn't deliver it to plants. So very heavy clay soils are often not really as good for agriculture as the little lighter soils. Some units here, I'll just go by this, but 105 kilopascals is 1 bar, so if you're used to using bars, that's the kilopascals, and 15 bars is about 1,500 kilopascals. The way we measure this most of the time, unless we're using tensiometers, which are used surprisingly quite a lot in California agriculture, for instance, and in Israeli agriculture. We use a granular matrix sensor and the gypsum block because these are easily data logged, and we can get telemetry of this data out of the field from the vendors. In both cases, we have either a gypsum block or a porous body of a granular matrix of graded sand. within a container, and in that we have two electrodes separated by a known distance, and we read the resistance within that block. That resistance is more directly related to soil matrix potential than to volumetric water content, which is why these tend to be calibrated in terms of matrix potential. The resistance decreases as the water content of the gypsum or granular matrix increases. And the gypsum itself dissolves and provides buffering of that soil solution, or the solution within the block. In the granular matrix sensors, we actually have a gypsum pellet included to provide that buffering. The buffering is important so that the conductivity inside the block is not greatly affected by the soil salinity, but there's still some effect. One of the problems with gypsum blocks is that they do degrade fairly rapidly in most soils and have to be replaced on a yearly basis, in some cases even more often than that. One thing to note is that you can't read these with just any data logger. You have to have a data logger that has an instruction to read these properly so that the reading doesn't polarize the electrodes and result in a false reading. Most of what's available now does it correctly. Here's some issues I've already discussed. Careful manufacturing is important, but what's out there now being sold is well manufactured. Some other issues is these are calibrated in terms of soil matrix potential, and I emphasize the conversion of this to water content is prone to large errors. Maybe more importantly, the range of readings is limited. For gypsum blocks down to about minus 600 kilopascals, which is nowhere close to the 1500 kilopascals of the wilting point, but maybe for the crop of concern within the management allowed depletion range. So these can be quite useful, but we need to know that they're not going to read all the way down to wilting point. And this is a little bit worse for the granular matrix sensors. They don't go down nearly as far as a gypsum block will. The most common problem that we see using these is that the sensor's soil physical and hydraulic contact can be broken irrecoverably when the soil dries. I was just talking with a fellow that was having this problem in California during fallowing. They had fallowed this field. They were going to irrigate it again. It was alfalfa, and they got their first cutting, and then they cut the water back, let it dry out because they were short of water, and they were going to try to re-wet it later in the season when the ET rate was lower and get another cutting. And the gypsum blocks, or the granular matrix sensors rather, just would not come back because that contact had been broken and they would not re-wet. This is fairly common. The other issue with these is that the sensing occurs in the sensor body, not in the soil. So we're assuming that there's equilibrium with the soil water. And this is not always true, and it takes some time for these sensors to equilibrate with changing water contents. Some advantages, and there are some real advantages, are that sensors and readers are relatively inexpensive. Telemetry is now available from most of the vendors. Installation and removal can be relatively easy, and economic loss, if we get a hit by machinery, is relatively small. In summary, all soil water sensors require soil-specific calibration, but calibration of capacitance sensors has been shown to not ensure an accuracy when the calibration is done in laboratory columns, and even when it's done in field soils. Electromagnetic fields from capacitance sensors do not uniformly interrogate the soil around the access tube or around the sensor, and this does lead to unrealistic spatial variation of water content. Effects of bulk electrical conductivity in bound water are not corrected in most electromagnetic sensors, but are much reduced with the time domain methods, such as TDR or TDT, simply because the frequency of the measurement is so large. The resistance sensors respond to soil water tension, but have limited range and soil contact, bulk EC and temperature issues. Now, I believe we're about out of time, and I think we can end there. I want to point out that Robert Schwartz here at our laboratory has done a lot of work on these sensors and is a very good resource. There are some references in this PDF file if you want to read more. And I'll turn it back over to Peter.
All right, thank you very much, Steve. We do have some questions, and if you do have any questions now, please, it'd be great to have some more questions to ask Steve. I'm going to start with one from Carl. Are any human health and safety concerns with any of these technologies?
The most obvious concern would be with the neutron probe. The health aspects of using the neutron probe have been studied very intensely over many years, and it's been concluded that the health risk is negligible, and we have the epidemiological studies to support that. Still, you know, you can't put a neutron probe in your pocket. You can't do dumb things with a radioactive source of any magnitude, but in routine use with training, those health risks are negligible. With the other sensors, the obvious things, electricity is involved, the voltages used are usually quite small, but there might be some power supply voltages that aren't, so one would want to be careful about that. The electromagnetic radiation from these sensors is quite weak, so there's not an electromagnetic radiation problem with the sensor itself. If there were a concern, it would be with the telemetry. And just as we may be concerned about cell phones, the telemetry radio frequencies and the intensity of the radio frequency fields is less than 1 watt in these, and it's pretty darn safe. You could fall down on one, you know, but beyond the obvious, no.
All right, thank you. Here's another question, and this comes from Bill, and he asks, is this statement correct? I think he just wants to see how well he understood this particular part of the presentation. So, TDR, TDT sensors are not significantly affected by soil type/texture, soil water chemistry, and temperature, even without calibration. So does Bill have that right?
Bill has that right. You can always find instances in which this is true, but for the wide range of agricultural soils, this is true. The effects are there, but they're much reduced to the point that one can say they're negligible if one can live with an accuracy of plus or minus 0.02 meter cube per meter cube. If one needs accuracy better than that, then one needs to use a soil-specific calibration, in which case one can do a little better.
All right, thank you. This is a question from Travis. What's the best method for judging soil moisture in soil with lots of cobbles and rocks?
Oh, that's a really good question. I can tell you what's routinely done, and whether it's best or not is questionable. With a neutron probe, we use a power auger, and we auger a hole larger than the access tube, drop it down the hole, and then backfill with soil that we sieve out of the cobble and rocks that comes out of the hole. And I've done this in river cobble and made it work. The reason it works is that the field of measurement volume around the access tube is so large that that annulus that we fill with that soil that we sieve out is relatively small in comparison to what the neutron probe is responding to. For any other sensor that's out there, this does not work well because the field outside of the access tube is much, much too small. In those cases, what people have done is simply dig down, try to find a place where they can get a sensor inserted into soil between the big rocks. And it's hard to do. We have this problem in the hill country here in Texas where the soil depth to limestone is very shallow. It's very difficult to get any kind of sensor in the ground.
Great, thank you. This question comes from Ken. What's the expected lifespan of a watermark sensor?
Oh, 3 to 5 years. That gypsum pellet will eventually dissolve. If your soil is basic in nature and pH greater than 7, it'll take longer. If it's acid at all, it might be quite a lot shorter. So in a more acid soil, you could see that gypsum pellet dissolve in a couple of years. And once that happens, then the sensor becomes responsive to a lot of things you don't want it to be responsive to, mostly the EC of the soil solution.
All right, thank you. This question comes from Richard. What is the most commonly used type of soil sensor in production agriculture today?
Right now, it's a toss-up between the capacitance sensors and the granular matrix sensors, our gypsum blocks. The capacitance sensors are very widely used because they're available, they're relatively inexpensive, there's a network to support them, and this is probably going to change as better soil sensors come on to the market. But it's only very recently that, one, people have understood the problems with these sensors and the theoretical reasons why they don't work well. And two, it's only very recently that better sensor technology using time domain methods have become available. There will be more of those. I think we'll see that change in the future.
Great, thank you. This question comes from Rebecca. What about the Decagon ECS and other inexpensive sensors, and specifically for sandy loams?
If you have a really sandy loam and there's no bulk EC, and if you're looking at rainwater, then they may work well with the soil-specific calibration. We tend to have problems with these sensors in heavier soils, and soils where we have saline seeps or other sources of salinity, or where we're irrigating in semi-arid and arid areas where we have an increase in bulk EC over the season. They may work well in those soils, but I'd be very careful because we've used some of those sensors, and certainly they don't work well here. So I'll let the buyer beware and check what your sensor is telling you.
All right. This question comes from Dan. Is slurry installation suspect for all sensor types?
For the neutron probe, as I answered in the previous question, a small slurry annulus is permissible because the volume of sensitivity is so much larger than that. The only other sensor types that go down an access tube are the capacitance sensors at the moment. There may be one come on the market that's a TDR-based sensor, in which case that one will be sold with the proviso that it not be installed with a slurry because it simply would not represent the soil. So yes, given what's available and out there, yes, that kind of installation is suspect for all kinds of reasons, but mostly the small measurement volume outside the access tube. Some of the vendors that started off in this in the 90s showed a diagram that showed that the measurement volume extended out 4 inches on either side of the access tube. Since then, that has been measured by us and others and found to be really untrue. It's closer to about 1 inch outside of the access tube. And it doesn't extend above and below the capacitance rings. It starts at the top capacitance ring and extends to the bottom of the bottom ring, but it does not go out further than that. So it's going to read mostly slurry.
All right, thank you. This question comes from John. What would you recommend as the best way for producers to reasonably determine trigger points for their irrigation with their sensors?
That will depend completely on the sensor. If the sensor is accurate, well, then we can be looking at what we know about field capacity and wilting point in that soil, and we can use some sort of a management allowed depletion. If we don't have that, and by and large on the market today we don't, then what we are really looking at is patterns. And because these sensors can be left unattended and can give us data every day or every hour even, and we can typically see that on the cloud, we can readily examine these patterns, and we can watch what's happening in the field and get some idea of what the response is, particularly if we've irrigated deeply and we see those values come up to a certain point. Do we really have to know what that value is? Well, one can argue that we don't have to know what the value is. We know it's pretty close to field capacity, or maybe momentarily went up above field capacity. If we're getting hourly data, we can usually pick out how that water quickly declined to a point that we would call a field capacity point. Once we've seen that with a sensor, then we can follow that, and the trick then is knowing when to irrigate. At what reading do we need to irrigate? And that becomes tricky. And what farmers are doing is that they're following the dynamics, they're responding to those, they're making decisions, they're irrigating when other indicators tell them that they need to irrigate, and they're learning what these systems tell them. The problems with that way of operating is that every time you install that access tube, every season, you're installing it in a different place and you're going to get a different result. You're going to get a different set of readings, different set points, and the farmer's got to learn every season what those data mean and how that can best be used to manage irrigation. People that really pay attention to the data can do a better job than having no data at all, and I think that's the bottom line.
Well, thank you, Peter and Steve, for your time and effort to make this presentation today, and thanks to all the participants for joining in. We had more than 310 people join today's webinar. Thanks again for your patience with the audio difficulties.